Let's do another example of curve sketching. I have y equals x squared over x squared plus 147, which I can kind of cleverly rewrite if I do plus 147 minus, if I do this, then I can rewrite this function as 1 minus 147 over x squared plus 147, which I can decide to use either one of these representations as convenient. What we're going to find is that, I believe we're going to find this is more convenient for the pre-calculus portion. This will be more convenient for the calculus portion. So looking at the domain and range, again, we're going to focus more on the domain and the range here. In the domain, there's nothing we can't plug in. There's no values that make the denominator 0, and x squared is a polynomial, so no issues here. So the domain is all reals. The next thing we want to do is find the y-intercept. So what we do is we plug in 0 for x. So if I plug in 0 here, I get 0 over 147. So that tells me that 0, 0 is the y-intercept. And since 0, 0 is the y-intercept, we know that it is also an x-intercept. But we still need to solve this equation to make sure there aren't additional x-intercepts. So we say 0 equals x squared plus 147. Since this is always positive, or just since it's not 0, we can multiply both sides by the denominator, and that gets us 0 equals x squared. That should be like a semicolon. And so if that tells me x is 0, so that tells me that this is also the only intercept. The next thing we want to do is look for symmetry. So to do that, this doesn't have any trigonometric functions, so we're not going to evaluate periodicity. But we are going to see whether or not plugging in negative values makes the function look like if it doesn't change the function, or if the only difference is that you can factor out a negative. So if I say f of negative x, so I'm saying this is f of x, then it's negative x squared over negative x squared plus 147, which is x squared over x squared plus 147. Well, that is my original function, so that tells me this function is even. What that tells me is I only have to consider the right-hand side. Once I graph the right-hand side, the left-hand side I just reflect it over the y-axis. So next, so in a lot of ways, it might be more advantageous to move this up the priority chart, because if this is up the priority chart, it saves you from having to find multiple x-intercepts. You could find the ones on the right, and then they're reflected on the left. But you do you. The next thing we want to do is look for any vertical asymptotes. Now, in this particular case, there are no values on which the bottom is 0, and there's no logarithms. So we really don't have any vertical asymptotes to deal with. The horizontal asymptote, now again, we only need to care about the right case because we know that it's going to be reflected on the left. So we say the limit as x approaches infinity, the limit as x approaches infinity of x squared, well, really, let's do this one, of 1 minus 147 x squared plus 147. Well, as x gets large, the denominator gets really large, so this term vanishes. The only thing left over is that 1. So that's going to be the line y equals 1 is our horizontal asymptote. Alright, let's continue on. The next thing we want to do is we want to get derivatives. So I'm going to go ahead and get some preliminary derivatives. Let's not even write that 7 here. Let's get some preliminary derivatives. F prime of x. So if I do like a quotient rule there, I'm going to get, so the 1 derives to 0. Over here, you could also rewrite this as negative 1 minus 147 x squared plus 147 to the negative 1. So then you would bring down the negative 1. So this would be 0. You bring down the negative 1 to make that positive 147. You'd subtract 1 from the power to make that negative 2. And then by the chain rule, so you would have positive 147 x squared plus 147 to the negative 2. By the chain rule, you get a 2x. So you could rewrite that as, what would that be? 294. 294x x squared plus 147 squared. Now we can continue this with f double prime. So for f double prime, I'm going to use this, and I'm just going to do like a product rule. So I'm going to say (294x x squared plus 147 squared). So when I do a product rule here, I'm going to get the derivative of the first one, hold the second one constant, plus the first one constant, take the derivative of the second one. Now this you're going to need the chain rule, so you bring down, sorry, that's a negative 2, that's a negative 2, and that's a negative 2. You bring down the exponent, so that's a negative 2. You subtract 1 from the exponent, that's a negative 3, and then you take the derivative of the inside, that's a 2x. So then when you combine this, what you're going to see is you have this x squared plus 147 in common. So let's see, you're going to get a common denominator of x squared plus 147, you're going to need 294 x squared plus 147 over x squared plus 147 cubed. And then in this case, you've already got that denominator, so you need to multiply all this out. So that was 294. You double that, you're going to end up with 592, no, I'm sorry, 588. You double that again, you're going to end up with 1124. No, that can't possibly be right. 588, and then if you double that again, you're going to end up with 1176, and so that's minus, so plus negative 1176. You have an x, so that's squared all over x squared plus 147 cubed. So then when you simplify this, you're going to end up with a, so these will, they're not going to cancel, but that'll subtract out. So that 294 comes out of 1176, so that's 976, 972, 882. Yeah, so that's going to be negative 882 x squared plus 147 over x squared plus 147 cubed, which we can factor out even more. We can pull out a 147, and I think we can pull out a 147. I think it goes into that 6 times. So you end up with square root of 6 minus x, square root of 6 plus x, all over, oh, that can't be right. That's going to be I apologize here. So that's going to be 1 minus square root of 6x, 1 plus square root of 6x, or x squared plus 143 cubed. Okay, so why does it look like that? Well, it looks like that because if I pull out a 147, what's left over here is negative 6x squared. So you have negative 6x squared plus 1. So that's a 1 minus something, a 1 plus something. So you split it into these two. So what that's going to do is that's going to help us solve for where the inflection points are going to be and where the critical points are going to be. So for f prime, the only critical point is at 0, 0, because this is always positive. So the only way it can be 0 is if x is 0 and the whole thing exists. There's no place where f prime fails to exist. So that tells me that zero is a critical point. Now we can do the second derivative test. So if we do f double prime at 0, if we plug in 0 to this thing, we get 0, 147 over some positive number. So ultimately, this thing is positive. So since that's positive, it tells me it's a minimum. Which, by the way, just thinking about this, you could have seen this without even using calculus. Let's take a look at the original function. This is always positive or 0. This is always positive or 0, which but the total sum of this has to be positive because that can never be negative, so it's 147 plus something. So if you have something that can never go below 0 and is always positive, then the floor of that function is 0. Anything else would have to be positive, which tells by construction, without any calculus, this has to be a minimum because there's no way. Because at the point x equals 0, it's at the origin. But it can never go below this. This has to be a minimum. We didn't have to use calculus here, but we did, and that's okay. The second derivative test worked for us. Now we have this, which tells me that I have an inflection point. So maybe I've done something wrong. I'm checking my cheat sheet here, and I want to make sure that I've done everything correctly. Now I had a negative here, and that's a problem because I didn't carry that negative. I didn't carry that negative here. All right, I didn't carry that to there. So if I didn't carry that there, then did I do this correctly? Well, that would, theoretically, that should just pull that to the outside. But I don't think that's going to do that. So one thing I did very, very wrongly, this was a very wrong thing that I did. Now I'm recognizing. And that's, bully for me. Is I have this 294x squared, which is great. But for some reason, I didn't multiply 294 and 147 here. Yikes. So this is actually 294 and 147, and it's actually that because of the way the negatives propagate. So then I don't actually pull out a 147. I have to get the greatest common factor. Well, but 6 goes into this, and that's 882, so that tells me 882 is my actual common factor. So that's x squared So if I pull a 6 out of this thing, it's going to be 49, which gives me 882 x minus 7 x plus 7, or x squared plus 143 or 147 cubed. Right? It's always, this stuff's difficult, man. This stuff's really difficult. So for points of inflection, there's no place where this fails to exist, because this is always positive, so cubing it's always positive. This is just some number. So it doesn't fail to exist anywhere, but it will be 0 when x is either 7 or negative 7. So what I have to do is I have to say, all right, positive 7, negative 7. So there's a really interesting thing here, though. We don't really have to check over here because we know it's an even function. So if we check over here, the behavior will have to match over there. Now, if I try the point of 0 and the point of 10, if I plug in 0 to this function, what I get is something positive over positive, and then a 0 here. So I get a positive value. So that tells me it's greater than 0. So that tells me it's concave up here. And then if I plug in 10, instead of plugging in 10 here, let's use it on this one, because that'll be 100 minus 49. Wait, what did I do wrong? Oh, this was negative. See, I'm not keeping up. So this was actually concave down. So like if I plugged in, I should have done it all here. If I plugged in 0 here, that was negative. If I plug in a 10, it's positive. So that tells me down, up, up. So now I have my points of inflection, and I need to evaluate. So I know that 0 is a critical point, so f of 0 is 0. We already knew that. And f of 7 is one of my inflection points. I know at negative 7 I also have an inflection point, but again, it's even. I don't have to care. So if I plug in 7, I get 49 over 196. 49 over 196 is actually 1/4. So I get 1/4 there. And then, so that tells me if I'm going to graph it, what do I have? I have no vertical asymptote. I have an asymptote at y equals 1. I have a point at 0, 0. I have a point at 7, 1/4. So from 0 to 7, I know it's concave down. And then it's up. That looks really odd. This shouldn't be right. My concavities are messed up. It's got to be up and then down. It's got to be. It's got to look like this. Okay, so walking through. The reason why this has to be true is if this thing was concave up, its derivative would be increasing all the time. If its derivative's increasing, you're going to have a hard time. So it's here. Your derivative comes down. Oh, this was positive. This was positive, which means this was positive, and this was negative, or was positive, which made this, man, I did all this so wrong. Which means I pull a negative out, I pull a negative out, pull a negative out. Which makes this okay, so I'm sorry, I apologize. There's been a lot of big issues here. So what's nice about this is because it's even, we can reflect it across. So you're going to get -7, positive 1/4, and it's going to come up and then over. This looks terrible, but I'm pretty stressed out from what is currently happening. So let me take a step back and say what's kind of neat about this is that I made a mistake, and I was able to recognize those mistakes because I have familiarity with this stuff. By the fact that I looked at this and goes, that just looks wrong. It looks wrong. My intuition's wrong because I've done it right enough amount of times. And that isn't a big pat on the back for me. That's an encouragement that if you can do this enough times, you, even when curve sketching, can go, that just seems wrong. That seems very wrong. And as a result, you can determine that, you know, the behavior just looks off. You know, I know that this should be concave up and then inflect and then have an asymptote, and it should have that because you're usually, I'm sure it exists, but you're usually not going to have something go up towards an asymptote while it's concave up, because if it did that, the concavity, the curvature is going to make it break through that barrier. It has to, at some point, plane off, curve away from the barrier. If it curves away from the barrier, it has to be concave down. So that's kind of how that works. That helps you out with that. But I apologize for all the mistakes, but mistakes are part of this. Learn from the mistakes, get better, become proficient.